In the last lecture, we have seen how to calculate the electric field intensity at a particular point due to the line of charge. Now, in this lecture, we are going to see the calculation of the electric field intensity due to the surface charge. So, let us start our discussion on the calculation of the electric field intensity at a point due to surface charge. Now, to calculate the electric field intensity due to the surface charge, here we have considered the Cartesian coordinate system, that is x, y, z, and on the xy plane the infinite sheet of charge is taken, and the charge density is taken as rho s in coulomb per meter square, and also we have considered or assumed that charge density is uniform everywhere. Now, to calculate the electric field intensity for the infinite sheet of charge, first we need to consider one elemental surface area, and that surface area we have considered ds1, here ds1, and which is present at the point 1 here. In this surface area ds1, the charge enclosed we can consider as dq, and here we have considered dqs, or also we can consider dq. Now, this dq can be calculated as the density into the surface area. So, dqs equals to rho s into ds. So, the charge enclosed by the surface area, we got that dqs. Now, we want to find out the electric field intensity at the point P, whose coordinate is 0, 0, h. To calculate the electric field intensity at the point P, we need to draw a straight line which is joining the point P to the point A, and which is directed from point 1 to the point P, and its distance is capital R. We know for a point charge the electric field intensity, or the expression of the electric field intensity, E equals to q by 4 pi epsilon naught r square AR. Here we can consider this ds1, that is the surface area, is a very small surface area or elemental surface area, so that can be considered as the point charge. That is why we can consider this equation. So, from this equation we are starting our calculation. Now, taking the derivative of this expression, we got dE equals to dq by 4 pi epsilon naught r square AR. So, now we are going to see that we are going to find out actually the AR by r square. Before that, we need to find out the r, this vector r. So, here to calculate the vector r, we need to find out the vector addition of this r, small r and h. Here you see that capital R equals to r into minus AR plus h az. How we are getting? You see that the direction of r will be from 1 to point P, direction of h from origin towards the z direction, and here you see that r, according to the cylindrical coordinate system, we know the direction of r will be from origin towards this direction 1, but in this case we need to consider the direction in from 1 to the towards the origin. So, for that it is r small r into minus AR. So, from that we got the vector capital R equals to r into minus AR plus h az. So, as we got the vector r, we can find out the magnitude of r equals to the mod of vector r. So, root over of this r minus AR square plus h az whole square. From that we can get r square plus h square whole to the power half, or root over of r square plus h square. Now we can find out AR. AR equals to vector r by the magnitude of r, that is equals to, you can see that vector r equals to RAR minus RAR plus h az divided by the magnitude of r, that is root over of r square plus h square. Now we know that we have seen in the previous slide that dq equals to rho s ds, and we know that ds equals to r dr d phi. Now the question is how we are getting r dr d phi. The answer is simple. If you remember the cylindrical coordinate system, from that we can calculate the ds. Here you see that again we are moving along the direction of r, that is dr, and if we move along the direction of phi, then the length will be equals to r d phi. So if you multiply dr into r d phi, then we will get ds. Here you see that r d phi into dr. So from that we get ds and rho s as it is. So we got the expression of dq. So as we got the expression of dq, then we can put the expression dq on the equation 3.2 that we got here. Again I have written here, you see that d equals to dq by 4 pi epsilon naught r square ar. So now again this ar by r square can be represented by r vector r by r cube. So here dq by 4 pi epsilon naught into r by r cube. So here we are putting the expression dq. So here rho s r d phi dr divided by 4 pi epsilon naught and r by r cube, we can get that from here. You can see that is vector r, that is minus rar plus h az divided by r square plus h square whole to the power 3 by 2, because here we have the r square plus h square whole to the power half. So if you multiply that is cube, if you take cube, then it will be 3 by 2. So expression of d we got, that is 3.3. Now interestingly here one point, it is very important to know that this term r into ar will be 0. Now the question is why? The r is 0 means what? The x component and the y component of the electric field E will be 0, only the z component will be present. So let us understand first that why this r component will be 0 and only the z component will be, we will get the z component. Then we will see the write up of this explanation. So let us move to the diagram again. Here you see that this is the infinite sheet of charge. On that we have considered ds1. For that ds1 charge, we can get the electric field intensity E at this point, and it is directed along this direction, AR direction you can say. Now as the electric field intensity is directed along this direction, then this electric field intensity we can consider E1. So this E1 can be resolved into three parts, that is along the x axis. Actually it is moving along this direction, that means the x component will be minus. So along the minus axis, minus x axis, along the minus y axis, and along the plus z axis. But as this sheet of charge is infinite, so everywhere we have the charge, so we can have the area, same area, which is opposite to the area of ds1, and the distance from the origin is same. So that point also we have, that is that area we are considering ds2. The magnitude of the charge enclosed by ds2 will be same as the charge enclosed by ds1. So for that ds2 we have also the electric field intensity, and that is directed along this direction, and obviously it has three components, and these components will be along the plus x direction, along the plus y direction, along the plus z direction. So from that E1 and E2 we can see that the x component, the magnitude of x component of the electric field E1 and E2 will be in the same, but the direction will be in opposite direction. So will be cancelled out, and also obviously for the case of y direction it will be cancelled out. Only the z component will be, for the E1 and E2 will be same along the z direction. That is why we can consider the x component and the y component of the electric field E for this ds1 will be 0, only the z component is present. So as the x component and y component is 0, that means the r component is 0, that is why RAR will be equals to 0. So here we have that RAR part will be 0, so only the HZ part will be there. So we will get dE equals to rho s r d phi dr h az divided by 4 pi epsilon naught r square plus h square whole to the power 3 by 2. That we will see in the next slide. Before that, the discussion which we have seen or we discussed, that is that we will see in the written form. Here you see that we can see the figure. Here you can see the figure. In this figure, uh, the electric field intensity E due to ds1 has three components, as I said: Ex along minus ax direction, Ey along minus ay direction, and Ez along plus az direction. Here also you can see that again in this direction, that means minus x direction, minus y direction, plus z direction. But electric field intensity for the same magnitude will exist at point due to ds2. As I said earlier, that the charge which we have considered, the sheet of charge which is infinite, for that if we have the ds1, also we have ds2, as the from the origin it is ds1 and ds2 will be in the opposite direction, but the distance is same. So here it is written whose distance from the origin is same as ds1 but in opposite side. Due to the elementary charge dq present in the elementary surface ds2, we will also get E at point P. Here again you can see that electric field E we will get due to ds2. So now if we divide this E electric field for the ds2 into three components, we will get Ex along the direction of x direction, Ey along the direction of y direction, and Ez along the direction of z axis. Now, as both the field intensity is equal in magnitude, then all the components will cancel out except z component, as I discussed earlier. So the r component will be 0, and here r component will be 0, and only the h component will be present. So here again you see that the expression we got dEz, because it is in the z direction, that is why Ez is taken, which is equals to, as I said earlier, rho s r dr d phi h az divided by 4 pi epsilon naught r square plus h square whole to the power 3 by 2. Now we are going to calculate the electric field E. So to find out the electric field, we are taking the surface integral, that is surface integral of dEz, that is surface integral of this term which we are getting. Now surface integral means we are moving from r direction and the phi direction. So here E equals to rho s by 4 pi epsilon naught, because rho s is constant, 4 pi epsilon naught is constant, so it is taken out from the integration, and phi will vary from its limit is 0 to 2 pi. R limit is from 0 to infinite, then r dr d phi h divided by r square plus h whole to the power 3 by 2 into az. So now taking the integration, first integration, and we will get the integration of this, we will get this one, you see that 2 pi we will get. So here rho s h, pi cancelled out, 2 4 cancelled, so we got 2 epsilon naught. And now if we take the integration of this expression, integration of r limit 0 to infinite r dr divided by r square plus h square whole to the power 3 by 2, then it is the standard form of the integration, and we can see in any standard mathematical books of the differential integration, that x into dx divided by x square plus a square into 3 by 2, that we will get minus of 1 by root over of x square plus a square. From that we will get, this is the integration, this is the standard form of integration we can get from any mathematical standard book. So here the limit is 0 to infinite. By putting the value of r once infinite and once 0, we will get 1 by h. So that expression, here the calculation in details is given here, I am not describing. So here ultimately by taking the integration we will get 1 by h. So ultimately E we are getting is to rho s h by 2 epsilon naught into 1 by h az. So h cancelled out. So electric field E at a point 0 0 h due to the infinite sheet of charge we will get equals to rho s by 2 pi epsilon naught az. Now the electric field intensity has only z component, if the charge distributed in xy plane. So now the equation 3.4 is valid. 3.4 means this equation 3.4 is valid if h is greater than 0. That means h is above the xy surface, and for that we need to use az. But if h is below the surface, xy surface, then we need to replace az with minus az, and for that case the expression here 3.4 will be E equals to minus of rho s by 2 epsilon naught into az, because we will get minus az. So in general the expression of the electric field intensity for the infinite sheet of charge we will get E equals to rho s by 2 epsilon naught into an. Here an is the unit normal vector and from the xy plane. So now if from the equation 3.4 and 3.5, it is the 3.5 and this one is the 3.4, we can see that the electric field is normal to the sheet. From that expression we can understand, and it is surprisingly independent of the distance between the sheet and the point of observation. This one is very much important. You see that the electric field is independent of the distance from the surface on which the infinite sheet of charge is present and the point of observation. So if we vary the point of observation along the z axis, the electric field intensity will be same. But the question is why? Now the students, that is the question is given to you. You should answer or you should comment why the electric field intensity will not vary for the infinite sheet of charge if we move the point of observation along the direction of z. So now we are moving to the second topic here, the electric flux density. We can see the definition of the flux, electric flux or electrostatic flux in terms of the electric field, that is given in equation 3.6, that is psi equals to surface integral of E dot ds. But the problem is that for practical reasons this quantity psi or the flux is not considered as most useful parameter in electrostatics. Now why? Because we can see from the we have seen from the derivation of the electric field intensity that the electric field intensity E is dependent on the medium in which the charge is placed, because you see that epsilon naught, it is the parameter of the free space. So electric field intensity is dependent on E naught. So if we change the medium, then electric field will change. So that is why it is not suitable to use this expression, the flux or the electric field intensity E. It is not at all useful in the case of practical calculations. So what we are going to see here, the electric flux density, which will replace the electric field intensity. So that is why hence we need a new parameter that is not dependent on the medium, and that is the electric flux density D, which is defined as D equals to epsilon naught E. And we can write in terms of the electric flux density D, the flux, total flux psi equals to surface integral of D dot ds. Now the question is how we can write D equals to epsilon naught E. Is it a speculation? No. We can find out that in other way we can understand this definition is valid. So here that other way we can say that this, you see that E equals to Q by 4 pi epsilon naught R square into AR. Now if we multiply epsilon naught in the both the sides of this expression, we will get epsilon naught E into Q by 4 pi R square into AR. Here you see that Q is the total charge and 4 pi R square is the surface area or the area. So if we consider a sphere, it has the area and charge enclosed by the surface area. So from that we can get, so the charge coming, due to the charge the electric field lines is coming out through the surface area. So if we consider the unit, the total charge, for that the electric field intensity or electric field lines are coming out per unit area, then we can consider it is the flux density. So this definition is valid, D equals to epsilon naught E. Now, as the electric flux is measured in coulombs, so the electric flux density should be measured in coulombs per meter square. Now, as we have seen that the expression of different expression we have derived or we have expressed, and also we have seen how to derive in terms of the electric field, that equations, all the equations can be expressed in terms of the electric flux density D. One example I have given here, suppose in the case of infinite sheet of charge, because we have studied just now. So electric field, we have seen the electric field intensity E equals to rho s by 2 epsilon naught into an. So that expression can be transformed or can be expressed in terms of the electric flux density, that is D equals to, you see that rho s by 2 an, because E equals to epsilon naught rho s by 2 epsilon naught. So epsilon naught, if you multiply both the sides, then we will get D equals to rho s by 2 into an. Similarly, for the volume charge distribution, we can find or we can replace the electric field intensity E in terms of D. So here D equals to volume integral of rho v dV by 4 pi r square AR. Epsilon naught is not present here. So this equation 3.9 and 3.10 shows that they are independent of the medium. So students, that is all for today's class. Thank you very much.